Hello, thanks for watching. This particular video is going to focus on something known as Hooke's law, which is actually an equation that describes the behavior of a lot of different kinds of springs. And so what I've done is I've drawn some situations on here to demonstrate how we would use Hooke's law. And I'm going to focus on both the force associated with springs as well as the energy associated with springs. And because my class is an AP C level class, I'm going to reference the equation reference page that comes with this class. And so looking at the mechanics side, I've numbered mine. I want to point out these equations here numbered 24 and 25. I'm going to write these on my paper in just a second. But this 24 describes the force associated with a spring. So you know just from your experience, every time you push or pull on a spring, it takes a certain amount of force, and that force can be calculated and described using this equation here. And also, we store energy when we push or pull on a spring. And so that energy that is stored is described here in equation 25. So let me write these a little bit better. And I will tell you just from my experience, the most common mistake students make is that they use the force equation where they should be using energy, and they use the energy where they should be using force. So if you're asked things specifically about force, or maybe you need to do a Newton's law kind of problem where you're drawing force diagrams and calculating accelerations, then you should be using what is commonly called Hooke's law, or the equation as it was written there on the reference page. It says F sub S, that's for spring. Sometimes this is called elastic force, so you'll see an E there, is negative K delta X. And both the force and the delta X have arrows over them, which in physics means that quantity is a vector, and you better pay attention to the direction. So this tells you something that from your experience with springs you already know. It means that if you, let's say, push on a spring leftward, that the force that that spring will push back is rightward. And that's the reason for the negative sign here. And if you, let's say, push in the other direction, then your force will change directions as well. So all this means is with the negative sign is that the force that the spring is exerting is going to be opposite the direction that it is either compressed or stretched. And then spring potential energy. Now I'm going to use a symbol here that you may not have seen before unless you've had some experience with other potential energies. And it's not unique, but I will say that different textbooks do it different ways. This particular reference page will use the capital letter U for potential energies. And in particular, this one is spring potential energy. And so it is described as 1/2 times K times this same delta X squared. Now we don't put a vector symbol over this one for a couple reasons. First, because it's squared, we just need the magnitude of the stretch or the squish. And energy is a scalar. It is not a vector quantity. That means we don't need any kind of direction associated with it. So something that I haven't mentioned yet, and it shows up in both equations, is this value called K. K is a symbol that represents the spring constant. Every spring has this characteristic. You might call it the stiffness of the spring, but it has a numerical value known as its spring constant. And the stiffer the spring, the higher the spring constant. Now see if this doesn't make sense. If you squish a couple of springs by 1 centimeter, and you feel that it takes a different amount of force to do that, that's because those springs have different spring constants. So the one where 1 centimeter causes a large force, that means it has a large spring constant. So, for example, the springs on a car that are part of the suspension of a car would be a very large spring constant. So hopefully you have some experience in your lab as part of your physics class if you're doing that, and you can feel some of these spring constants yourself. So let me show you what I'm going to do with these three situations down here. I'm going to imagine that I have this spring in its what we call its relaxed or its equilibrium state. That means if I let go of this 5 kilogram box, it's just going to stay put. And so what I did is I put some markers down here to show maybe what the meter markings are, and I just called that resting position 0. Now, in this state, I would say that I have no spring force on it, and I have stored no spring energy. And that's what we mean by this relaxed state. But what about these other two situations here? If I were to take this and push it leftward so that the left edge moved 3 meters, now I have a force exerted on the box by the spring, and I have some energy that I have stored in the spring and the box system. I can calculate both of those as well. So let me do them one at a time. The force that the spring is exerting on the box can be found with the equation up here. That's the Hooke's law equation. And we have to give the spring some kind of spring constant. So I'm going to choose a nice number like 15 newtons per meter, choosing convenient numbers that won't make the math too weird. So I don't have a lot of room to show the calculation, although I might squeeze this one in. So I've got a K of 15 newtons per meter, and my delta X, notice I've gone leftward 3 meters, so I'm going to say negative 3 meters. And when I multiply those, I'm going to put an arrow symbol over this to remember that that's a vector. So I'm going to get 45 newtons of force. And that comes out a positive, which tells me that the spring is exerting a rightward force, as we would expect it to if we squished it leftward. So that's my spring force. How much energy has been stored in the spring? You know, if you remember about energy, if you've seen it before, you can store energy in something, let's say by taking this 5-kilogram block and lifting it up 3 meters. And then we've stored what we call gravitational potential energy. But this, I'm not changing its height, I'm just changing the compression of the spring. So this spring energy is 1/2 K delta X squared. So it's the same K and it's the same delta X, but obviously we do something a little different. I am not deriving this equation, by the way, because it's going to take some calculus. I don't really want to bog down this video with the calculus. If you need to see a demonstration of how we derive that, I may show it on another video, but you might also find it in a different reference. So if we plug in the same K and the same delta X and we square it, then we're going to get 67.5, and that's a unit of energy, which is joules. This energy will never come out negative. If you look, K is always going to be positive and delta X is always going to be squared. That means we're never going to have a negative energy. And that's always true for springs. Now, that's not true for gravitational potential energy, but that's got a little different setup. So just know if you get a negative spring energy, you did something wrong. So imagine now if I let go of this 5-kilogram box. Now this box is going to want to fly rightward because of that spring force exerted on it. But notice this spring force is not going to be 45 newtons the entire time. As soon as I let it go and the spring starts to stretch out a little bit back to its relaxed state, that force is going to go down the entire time. So we could ask, maybe after the left edge gets to -1 meters, now how much force do we have on there? And it's calculated the same way. I've got the same K, but now my delta X, how far I am from my relaxed position, is just -1 meters. So that's going to give me just 15 times 1, or 15 newtons. So being squished 1/3 as far means only 1/3 of the force. But watch what happens here with the energy. This is not a linear relationship. So here's again another mistake students make is the delta X is how far it is from its relaxed state. It's 1 meter from its relaxed state. We would not use the 2 meters that it has moved from here to here. So when I plug in 1/2 kx squared, I get only 7.5 joules. That's a very tiny fraction. In fact, roughly about 1/10 or so of the energy that I had stored when I had moved it just 3 times as far. So what might I do with this? Well, what if somebody asked, well, how fast is this box going to be going once it gets to this position? This is the perfect time to use conservation of energy. So if you've seen my other videos, you know we could make a little energy table here. This might not be necessary for this particular problem, but I'm going to move it up so you can see this. So I like to make an energy table showing all the different forms of energy I have. I've got kinetic, and I've got spring potential energy. I'm not going to include gravitational potential energy in this problem because I have no changing gravitational potential energy. And I'm going to have a line for the total as well. So what I do is I make a table for my initial values. These will all be in joules. And then my final value, it doesn't have to be initial and final as if everything's done, just initial and final for the part of the problem that you're asked about. So I started, let's say, at this position here. When I let go of it, I had no kinetic energy, but I had stored 67.5 joules of spring potential energy for a total of 67.5 joules of energy. But when I let go and I move it back here to the -1 meter position, then I calculated I only have 7.5 joules of energy. Now I didn't state it, but we'll just assume that this is a frictionless surface. We don't have any forces that would be removing any of the mechanical energy. So I can call this a system where energy has been conserved. And so I can also write 67.5 joules of total energy at the end. Well, now I can see to have 67.5 joules of total energy, I'm going to need 60 joules of kinetic energy. So how fast does this object have to be going to have 60 joules of energy? Got a little bit of space here, hopefully you can see. Remember, the kinetic energy is 1/2 mv squared, or a lot of times we use it in this form. The velocity is 2 times the kinetic energy divided by the mass and then square rooted. And I'm going to save a little bit of space. I would think you as a student, you would be writing this out so we can see it clearly. Show me the substituted numbers, etc. But you can trust that I've done this on another piece of paper. I get about 2.8 meters per second. And again, that would be the speed that it would have once it's gotten back to this position here where its left edge is at -1. Now I would challenge you, I'm not going to show this in the video because I've gone much longer than I'd like to, but if you just calculated the amount of energy using 2 meters, because a lot of people would do this, they say, well, it moved 2 meters, I'll just use that for my delta x. That is not the same as finding the difference in the stored energy compared to the relaxed state. So I just want to urge that. Everything has to be measured from the relaxed or the equilibrium or the resting location of your spring. So I think I'll leave that there. This has gone long enough, but I've covered a lot of territory here, and hopefully that helps you when you get to some spring problems of your own. Good luck.